Because yep, we do. Thomas, Nicholas.
Hey there. Can you hear me okay?
Yep, we can hear you, and I would still ask Eric to make you a co-host so we can share your screen.
Okay, great. Thank you.
And you've got the last lightning talk of the week, and this would actually be a sort of meta talk on the progress of the whole community. And I think everyone here is going to it's going to be a nice change from all the other talks we had. Well, Thomas, take it away.
Thanks, Tom. So what I want to talk about today is a project in the geosciences, the climate sciences, and what I think the plasma physics community can learn from it. So some important context is that I just defended my PhD in scrape-off layer turbulence, working with CCFE and Fusion CDT, but I've also just started a job as a research software engineer at Columbia University in Lamont Doherty Earth Observatory, which is like a geosciences lab near New York. So I've kind of got this insight into how two different fields of science are trying to deal with similar computational problems, which is what I'd like to talk about. And also, I'm on the X-Array core development team. I understand there was an X-Ray tutorial the other day, which I unfortunately couldn't make, but that's great. So if you take anything away, it's that the plasma physics community should copy the Pangeo project. I'll explain what the Pangeo project is and its particular software ecosystem, because I think that in general, that project is doing a good job at dealing with some of the problems that we as researchers still, in my opinion, struggle with in fusion in general. A lot of what I'm going to say crosses over very heavily with the aims of Plasma Pi. So I guess the purpose of this talk is to say, here's an example from another field, and we can compare and contrast and see what we could learn from one another. Not that I think that Plasma Pi isn't already doing a lot of things that I'm about to suggest. So what is Pangeo? This is going to be the structure of the talk. What is Pangeo? Why should we try to emulate it? And how can we start doing that? And this talk is a summary of a blog post, which I've put up here. So what is Pangeo? Pangeo describes itself as a community platform for big data geoscience, but really it's multiple things bundled together. It's primarily an ecosystem of open source software libraries encouraged to interoperate with each other. But it's also a network of users and developers in the geosciences, and there's like a discourse forum and other platforms for people to ask questions and communicate about how to push their software forwards. It also provides some things which I don't think Plasma Pi does at all. So they have an open online data catalog, which is particularly important in the climate sciences because you often have satellite and reanalysis data sets that multiple users want to pull down and then analyze. But Pangeo is also pushing another aspect forward, which is cloud-based computing. So their aim for big data geoscience actually revolves around not having to pull the data down, and instead you take the compute to the data, so to speak, and do your work in the cloud. And Pangeo provides some tools to allow users to do that. The explicit goals of the project are to foster collaboration and create a scientific Python ecosystem, and then build on top of that with domain-specific packages that people in climate and ocean and earth sciences would want, but other people wouldn't necessarily want. And also, crucially, to work out how to scale this to huge data sets, which is a considerable challenge. But is really scientifically important when we keep getting more and more data from larger simulations and higher resolution diagnostics. Pangeo's already quite young, but already very successful. It's used by major national meteorology labs, including the UK Met Office, which is basically one of the best places in the world for weather forecasting. Pangeo has hundreds of regular scientist users on top of that. It's rapidly becoming the primary way to access what's called CMIP6 data, which is the coupled model intercomparison projects, which are basically all of like the world's different models of how climate change is going to play out. And the researchers who compare and contrast those models and do that modeling, a lot of them are moving towards using Pangeo to access it. So it's becoming like a key linchpin within the climate science ecosystem. Literally yesterday, I was talking to a guy who described the whole thing as the most helpful thing to have been made for his research in the last decade. So why should we in the fusion community emulate Pangeo? I submit that geosciences and plasma physics are very, very similar as scientific fields. Obviously, in one case, you're dealing with something that's 100 million degrees hotter than the other case, but computationally, both deal primarily with very large, like much larger than your RAM, multi-dimensional, like time, latitude, longitude, or different axes of a tokamak, or even different like directions in velocity space. Quasi two-dimensional, fluid turbulent data sets are all very common. In both cases, you have regular rectilinear grids, but they're warped in some way because of either magnetic curvature or the curvature of the Earth. You often want to pull that data from some central lab server, whether it's because it was a shot run on D3D or because it was satellite data that was then put up on a central server. And you often then want to compare your pulled experimental data to some simulation data. We know that plasma software in general has problems, and these are some of the problems that efforts like PlasmaPy try to solve. My personal experience in my PhD trying to run simulations and analyze them with the tools that are available is that for most of the magnetic confinement fusion community, at least, code is not regularly open or shared. There's a lot of examples of reinventing the wheel. Especially because we don't take advantage of existing solutions. And I think there's a bit of a cultural problem where in some labs you feel that because fusion as a general engineering challenge is extremely difficult and niche, that means that we must need bespoke software tools to deal with it, which I do not think is the case. And I think, in fact, we should be taking advantage of libraries from other fields as much as we possibly can. There's also just that you all know that there's a lot of legacy code in fusion research, particularly a lot of IDL still used in analysis at CCFE, for example. And all of that means that nobody's really thinking about how to scale this up to like petabyte size. But the Pangeo project has already largely solved a lot of these problems. Like all of the software packages that people are using for analysis are open, which facilitates sharing of tools. It's built on top of some very powerful domain agnostic tools, particularly X-ray for labeled multidimensional data, Dask for parallel processing, ZAR for cloud optimized storage are some of the main ones. But the way that it's all built together means that you're not really tied. You don't have to use any one of those. If you want to swap them out, then you can, because the APIs are what's standardized rather than having one domain specific stack that no one else can plug in and out of. And that has huge advantages because it means that you don't just have people from your own research field working on making the software better. It means that you have like random people from finance and stuff come in and they're like, oh, this is useful. Here's a pull request to make your library better. They use modern code, modern software practices. Lots of talks we've been heard about that in the past week. And the scalability is built in from the start. And that's my specific research work in my new job is to do with trying to execute analysis workflows on literally petabytes of ocean simulation data. If we created our own packages in a way that we could plug in to the parts of this ecosystem that would be useful for us, we'd get some immediate and very large wins. Dask in particular is an incredibly powerful library providing parallel and out-of-memory analysis. It stands for distributed tasks, and essentially it takes some task you want to perform on an array like a mean and splits it up into chunks, each chunk of which is sent to a different parallel process and then recombined at the end. And that alone is crucial for scaling up. But we also get a bunch of other wins, which are discussed in more detail in the blog post, such as cloud optimized storage, labeled dimensions, unit-aware arithmetic is coming very soon. All of this, having all of your different analysis packages all being available on GitHub and version control and everything, makes reproducibility far easier because it basically means that the Conda environment specifies your entire analysis environment. You can plug in more easily to nice plotting packages like HoloViews, which is very powerful. And there is a lot more focus now on machine learning integration as well. And there's some glue packages like sklearn, X-ray, for example. So if we wanted to make something similar to Pangeo in plasma physics, how would we go about that? So I think what we need is, I think personally what we need is more emphasis on having modular and interoperable packages. So one of the reasons that this Pangeo stack works really well is they've got very good at having a large number of small packages that each does one thing really well, but don't tie you into having to use that solution. Building on top of powerful tools with a specific API, in particular X-ray. So all their geoscience specific stuff goes on top of that. So, for example, you have things like CartaPy, which essentially does nothing but provide map projections of the Earth's surface from, obviously there's multiple ways to get from sphere to a flat plane, and CartaPy as a package just nails that one problem, but doesn't tie you into using anything else. So it can be plugged into all sorts of plotting frameworks and doesn't assume much about the underlying data. Similarly, keeping domain-specific functionality decoupled helps with this. And I also think that we should be thinking about moving to the cloud in a similar way. So specific things that I think should exist, and I've given a little, in the blog post, I've given a little bit more detail as to what each of these might involve. Some kind of single tokamak data model, ideally based on NetCDF's like specification and X-ray. I mean, OwnFit already does this to some extent behind the scenes. One thing that we don't have in Fusion that they do have in climate sciences, which is incredibly helpful, is there's this thing called the CF conventions. And the CF conventions are basically just a universally agreed upon way to write out particular units and particular grid types in the attributes of your data, so that when you load data from some other simulation code or something, then if that data is CF compliant, it means that you can be confident that when you load it, then the units are what you think they are. They're in electron volts rather than whatever, or the equivalent in geosciences. And I think we should be aiming to reach that kind of standardization in the plasma community as well. And it's formalized through this like separate website that says exactly what the CF conventions are. In some ways, having clear specifications is almost more important than having code, because the clear specifications are what allow you to swap new coding solutions in and out painlessly. I think there's space for a tokamak specific plotting package like the CartaPy globe Earth projection package that I mentioned. Like almost everybody ends up reinventing code to plot data for a tokamak, which is silly. Everyone should just be importing one package and then using that to make all their slice plots through different planes of a tokamak. There's also potential for clever indexing of X-ray objects, common analysis tools. I mean, this is something that PlasmaPy is doing really well. And then what makes all of this work is to have code-specific compatibility layers. So to give you a specific example, in my PhD, I used the Bout++ simulation framework for boundary turbulence that some of you might be familiar with. And I basically made a compatibility layer that would take any Bout++ output data and return it in the form of an X-ray data set, and just doing that allowed me to then use all of these like really powerful tools in the wider ecosystem immediately. So in conclusion, and I welcome questions, I'd love to talk about this more. I think that a very successful model for open source scientific software ecosystem already exists, just in another field. And because it's scientifically very similar to plasma physics, it maps intuitively onto similar plasma problems. And if we try to emulate a similar ecosystem and integrate them together, then we could combine the powers of our two research fields to end up with better software than either might achieve on their own. Thank you.
Thank you, Thomas. That was a really, really, really cool talk. And I think you've located all the nails and hit them right on the heads for the community. I mean, yeah. We do have a couple more minutes. Okay, if I could ask you to copy the public-facing blog post link, maybe into the chat.
Yep, I'll do that now.
Awesome. Thank you.
Oh, I haven't
I
been
think
looking
we
at
have
this.
a couple moments for questions. Okay. Awesome,
I'll
thank
just
you.
I'll just have a look back through the chat. Pangeo, interesting.
And Nick, you're not audible. You're unmuted, but not audible. For some weird reason. Is it just me or?
Can you hear me now?
Yep.
Okay. Yeah, Panhelio was something that was brought up for as like a grant proposal idea, I think, last Monday. But there is a lot of interest.
Mm-hmm. Great. Yeah. So as I said, I mean, we're all here because we agree with a lot of these aims, right? Like there is clearly a lot of crossover with Plasma Pi, and I'm not trying to suggest that like Plasma Pi and Pangeo and UNFIT aren't already thinking along these lines. I'm more just saying that like we don't have to feel around in the dark. There's this really successful solution that are very open about how they're doing it and what they're doing that we can look at and we should be looking at to try and learn as much from as possible. And they want other people to be using their tools as well, because if other people are coming in and using things like X-ray and Dask, then they benefit. Everybody benefits.
So I got a question, or at least question to have you elaborate more on. So I agree with everything you've said, and I think they align fairly closely to what we're trying to achieve in Plasma Pi. Now, the difficulty I've always had is something like this, since there doesn't seem to be a real head behind it. Can you make any comments on turning a great idea into action?
That's a good question. So my new supervisor at Columbia is one of the people who basically came up with the Pangeo project. And it built up bit by bit, but part of it was pushing for specific use cases, like a rather than just like a satellite series of software packages. There was like, I will ask more about how it originally got set up, but my understanding was part of the way it got set up is that there'd be a grant application for like big data oceanography or big data plasma physics, right? And then as part of that, then it would encourage the development of certain tools, which would kind of give a sort of flagship and an impetus rather than a bunch of individual software developers essentially doing it on the side. And I think that was one way in which like it was formalized and pushed forward. I'm not sure if that answers your question.
I think it's going to where my head was at. I almost feel like to achieve something like this, there needs to be some kind of committee out there that.
Oh, there's a Pangeo steering committee. Yeah, definitely. Yeah, and you need some equivalent.
Yeah, and so it orchestrates what packages are out there and possibly even orchestrates standards to some degree. I would say the closest that we've tried to do at Plasma Pi, so I know that the Plasma Pi name is becoming more and more widely known, and we want to be able to use that as an advantage to advertise all open source projects and not just ours. And so I know one of the things that we've put on our website that hasn't got much adoption yet is actually, if you go to the website, there's a section on affiliated packages. So this is a place where we want to be able to list all different projects out there. And so I would say if there's anybody here that is interested in the idea, to go to the website that Nick just posted in the link, and there's a form for you to fill out in which we can put you on there. And at least, I mean, like one of the big issues is people don't know what's out there. And so to at least bring it all into one spot.
Yeah, I think that definitely helps. There's also there's a public discourse which is worth looking at, a discourse forum for Pangeo, and it's worth looking there because you get some idea of how they make decisions and how it kind of presents to the wider community through that, which might be useful. Sterling asked, are you aware of IMAS for tokamak data model? I'm aware of IMAS. I've never used it personally. I'm talking about the ITER's integrated modeling analysis suite, right?
Well, I mean, there's the IMAS suite, but then there's just the data model itself that is more useful.
To what extent is the data model compatible with this kind of ecosystem? Do you know?
Well, the biggest hurdle right now is that it's presumably been created by ITER and therefore is subject to ITER licensing.
So it's not fully open source?
It's not fully open source, but as far as I can tell, everybody is pushing for it to be open source.
Right.
I asked David Koster about progress on that the other day, and he said that basically we need to get somebody at the ITER council level. So basically from the US, like the department, the secretary of the Department of Energy, to bring it up at the ITER council level.
Right. Interesting.
So I think everybody on boots on the ground says, hey, let's make it open source, and then just has to go through this other hurdle.
So until that happens, IMAS, the format is sort of close, like PDF in a sense, right? Everyone uses it. It's pretty much closed source.
Well, does everyone use it? I mean,
okay, yeah. I mean, everyone. No, okay.
Yeah.
I overstepped there. Right. A lot of people are pushing for everyone to use it.
So, okay. So, I mean, my knowledge of the internals of the IMAS analysis suite is small. So, but what I would personally like to see is there's this issue of standardizing a data model, which would be hugely helpful if that were done. But then there's also how is IMAS code actually like implemented under the hood? And from what I've heard from friends who work at ITER, then a lot of it is like custom built specifically to handle problems and is basically not particularly interoperable with a wider ecosystem. Whereas what's really enabled Pangeo to like grow organically is this interoperability. And so what would be nice is if such a standardized model were compatible with a more modular system. And so that if IMAS people wanted to actually swap out some of their underlying code for open source packages, then they could. But if they didn't want to do that, then it doesn't interrupt what everyone else is doing either.
Right. Yeah, I certainly agree that the whole IMAS software stack is it's very tall and somewhat cumbersome. So I was only referring to the data model.
Yeah, no worries. Just trying to make a sort of separate point. But that's also how like I see this idea relating to OMFIT, right? Because OMFIT obviously, if there were a pan-plasma ecosystem that provided these different things, then OMFIT would be able to just import packages that are also available to everybody else and to some extent they already do this. But it would make the ecosystem more robust if more of it was done like that.
Yeah, absolutely. Yep, and that's where OMFIT is headed, is trying to work with packages that are using IMAS as its data schema.
Yeah. Great. So there's another thing that's interesting that I might elaborate on a little bit more. I don't know if there's more time here. I'm not really sure. Is this whole idea of moving stuff into the cloud. So one of the original motivations for Pangeo was the release of this like unprecedentedly large and high resolution ocean turbulence data set that's literally like multiple petabytes. And the problem is that like it's hard to analyze something that large, even on like a cluster or supercomputing node. And you want to do that in an open and scalable way, ideally. So there's a lot of tools that go in. So there's X-ray, but then there's below that, there's sort of virtual file system access libraries like FSspec. And then there's ZAR, which is like, it's kind of like you could swap out NetCDF for ZAR. And the idea is that ZAR is like chunked and compressed on disk so that it enables like parallel reads and writes like really efficiently. And the idea is that by doing this in the cloud, so this Pangeo stuff is basically runs on like Amazon Web Services and Google Cloud Storage. So you end up with this interesting dynamic where instead of the department owning or like renting time on a supercomputer, instead you just spin up some Amazon Web Services like Bucket or whatever when you want to do the analysis. And then what's so clever about libraries like Dask is that if you want to do something more computationally intensive, they can dynamically scale up and request more and more resources. And that's really nice because it means that you don't have to like pre-decide how much compute power you need to get a certain job done. You can just, the analysis, the scientists on the other end can just like dynamically request more when they need it. And if you had perfect parallel scaling, it would basically mean that the time it takes for the user to do the analysis has been decoupled from, it essentially becomes constant regardless of the size of the data set, because you just recruit more resources when you want to do something bigger, which I think is really powerful because our largest expense is like staff time rather than compute power. And a lot of scientists, and the problem that like OMFIT tries to solve, right, is that a lot of scientists just don't want to have to worry about the details of that. They just want to like hit compute and hit plot on some big data set, and they want that to just work. And the fact that that's actually doing something amazing behind the scenes with like cloud storage and terabyte data sets and stuff, you just want to abstract that away from them as much as possible. And that's what this cloud stuff like really allows you to do. So yeah, it's just some more food for thought there.
There's a good question in the chat about the source of funding for the cloud computing resources. So how's that organized?
That is a good question that I assume is like a data science grant, but I'm not sure. It might also be, there's a national lab, Lamont Doherty might be paying for it. But to be honest, I don't actually know. I could find out though. And it might be on the website. But if these sorts of questions, if anyone wants to go on to the discourse is open and anyone can sign up. If you want to go on there and say, we're fusion physicists, we're interested in how you're doing this stuff, we have a couple of questions about like how you even got this started, they would love that. I think that would be really worth doing.
I think we're going to definitely have to reach out. Maybe not this week because, but yeah.
Great.
That is definitely amazing.
Well, please tag me or CC me in when you do, because I'd love to be a part of that.
Of course.